So that's the assessed practical. And you find the protocol, as I said. Oh, good evening. You find that in your lab book. Let me just quickly see if I have it here. So your task tomorrow is, you're working on your own, so not in pairs. You're working on your own. First, you have to prepare a standard curve. And this standard curve actually should be a straight line, ideally, where you have known amounts of bovine serum albumin. You let this bovine serum albumin react with a standard reagent, which is this BioRed reagent. And you can read more about the theory in your manual. Good evening. And what you then get is different colors depending on the concentration of your BSA in the solution. And you just simply put that into a spectrophotometer and read the absorbance of these different concentrations. So here you've got your table of the things that you have to mix together. So for example, in test tube number 1, you have no serum albumin, so you can immediately do your concentrations that you have in here. And you go up to 1 milliliter of the serum albumin, and you let this react with the reagent, with the BioRed reagent, and what you should get then is, depending on your amount of BSA, and that would be amount in milligrams, and here would be the absorbance. What unit does absorbance have? Doesn't have any unit. Excellent. What you should get is basically a straight line. Well, this is as good as it gets for me, a straight line, where you have basically certain amounts of BSA. And from this straight line, you can then do it backwards and discover the concentration, or the amount of BSA, I should say, the amount of BSA which is in an unknown solution. So, for example, you find that your unknown solution go away. Your unknown solution has, let's say, an absorbance of this here, whatever this is, and you just simply look at your standard curve. You just go to the right and then down, and you can measure what this unknown sample, how much of the BSA this unknown sample contains. Yeah? It's pretty straightforward. So you do the standard curve. Shall we quickly calculate the amounts of BSA that you have in these different samples? So in the first one, you don't have any BSA, so the concentration would be 0. Thank you. The second one, you have 0.1 0.1 milliliter of 10 milligram per milliliter solution. How many milligrams do you have? I get mixed messages here. What do you get? 1. Thank you. Just, let's do milligram. We have 10 milligram per milliliter times 0.1 milliliter. Milliliters cancel out, so you have 1 milligram. So 1 milligram. And in tubes 2 and tube 3, 4, 5, 6, 7, 8. Good. So I've done that for you now. So you just have to copy it tomorrow. Right? Okay, so you do that, and the way you do it is let me see if I find that. You add to your 8 tubes that you have with the BSA, you add 7 milliliter of the bioret reagent, mix well, and leave it for 30 minutes. Right? It's important that you leave it for 30 minutes. You can leave it for longer, but don't just do it immediately after you added the mixture. Okay? And then you should measure it, and it should give you a nice straight line. You are also provided with some unknown samples. So each student will get sample labeled either A, B, C, D, E, or F. Right? And let's say you have picked a sample labeled C. So what you do is, in 3 different tubes, you add 0.2 milliliter. So you perform this experiment in triplicates. And you set it up like this here, each one of them. And you add also your 7 milliliter of the bioret reagent. Do this at the same time as you set up your BSA standard. And then you simply measure the absorbance. And as I said here, what you should get is a straight line with your standard. Okay? And you get basically 3 different absorbances for your 3 samples. They are all from sample C or A or B. So don't try to do all 6 of them. It's just either A or B or C or D or E or F. Last year we had some specialists who did everything 3 times, and they said, I don't have enough time. Read the manual. And you can do it either. You can use the 3 different absorbances and calculate the mean, and then do your measurement from the standard curve. Or you can do 3 measurements, get your 3 values for the milligrams of BSA in your unknown sample, and then do the mean of it. Doesn't matter which way you do it. Yeah? So, once you have done the mean, so you get your mean from that, you need to calculate what your BSA concentration in your sample was. So let's say you find that your sample here, this one here, was equivalent to, say, 3 milligram of BSA. Yeah, that's the mean. And you know that you had these 3 milligrams in this 0.2 milliliter. So then you can easily calculate the total concentration of BSA in unknown sample, BSA in unknown, would be 3 milligram in 0.2 milliliter, because you just used 0.2 milliliters, and that gives you, what does that give you? Loud? 15 milligram per milliliter. Yeah? So that would be your answer. Concentration of C is 15 milligram per milliliter. I also then want you to do a standard deviation. And again, you have the equation for the standard deviation in your manual. In this case, we use the population standard deviation, where you take the 3 data points, subtract the mean from it, square it, and sum it up, and divide it by n. Okay, not n minus 1. That would be the sample standard deviation. You use the population standard deviation in this case. And you can also calculate the standard error of the mean, which in this case would be your standard deviation divided by the square root of n, which would be 3. Okay? Happy with that? What I would expect is that your graph is indeed shows a straight line. You need to label the axes as it says in the protocol. You have to use sensible numbers. And you will be assessed on how accurate your graph is. Does it give a straight line? Have you calculated the concentration properly? Have you done your standard deviation properly? Have you done your standard error of the mean properly? And does your graph look good? Does the graph have the right labeling of the axis? A title would be nice. For example, standard curve to of BSA to determine an unknown concentration of BSA. And the last thing that you will be assessed on is whether you wear safety specs and gloves at all times. If you don't do that, you will get a deduction in marks. Okay? Task clear? You can do it? Traditionally, students score around 80% in this assessment, so that's the average. So you bag your first class mark with this simple practical. Okay, happy with that? Fantastic. Any questions? Or is it clear as mud? Yeah. How much does this count? I think it counts 30% of the coursework. Does it get any easier? Not really. Okay. Let's see. Let's see if we get the second hour now in this one as well. Right? And I spoke a little bit about your graph. So let's say absorbance. And here you have the milligram of BSA. Oh, by the way, why does this graph go through 0 here? Why does it go through 0? When it's no BSA, it still has a color, but what you do with this sample here, you zero the spectrophotometer. You use that as the blank. That's quite important, yeah? Use this as the blank. Because then you tell the spectrophotometer, this is supposed to be 0, and that's why the graph should go through 0. Yeah? Okay, now, what you probably will discover is that the first point here will go through 0, because you told the spectrophotometer that it's 0. And then you do your measurements. Which might look a little bit like that. It's probably not exactly a straight line. How are we going to deal with that? Well, most of you have heard of a line of best fit, right? Do you know how to do that? How do you do that? Sorry? Equal number of points either side. Right, let's do something horrible to you. We have one that is really bugging us, isn't it? So what you can do is actually, you can do it by eye. You can say, okay, let's... Yeah? Something like that. Would that be accurate? Relatively? Sort of? Yeah. Now, what we are now talking about is actually a correlation. We derive a correlation between an independent variable So what we plot on the x-axis is independent, whereas on the y-axis we have the dependent variable. Dependent because it depends on the independent one. So the independent is chosen by me. The dependent one is a result of the independent variable. Right? That's just as a bit of terminology. Now, obviously looking by eye is all right, but it's a little bit unsatisfactory, isn't it? First of all, what kind of correlation do we have here? Loud? It's a positive correlation. Well, what do you mean by positive correlation? The higher the independent variable, the higher the dependent variable. Yeah? So if your line goes like that, goes up like that, this is a positive correlation. What would be a negative correlation? If it goes down. So let me draw this here. So this would be a negative correlation. So positive correlation we come across every day. That would be, for example, temperature. The temperature and the sale of ice cream. The hotter it is, the more ice cream you sell. It's a positive correlation. The colder it is, the less ice cream you sell. The hotter it is, the less hot chocolate you sell. The colder it is, the more hot chocolate you will sell. Yeah, these are, for example, nice visualizations of a positive and a negative correlation. How do we determine these things? Independent, dependent variable, and we've got something like that. Now, how can we measure how good our line of best fit is? Any ideas? How can we measure that? Sorry? The R point. Yes, you're absolutely right. What we are going to do is we use the Pearson's correlation coefficient. And the way it works is we basically measure the distance of our point here, of this point, to the line. So the distance of this point to the line would be this one here. Yeah? And we do that for all points. So we've got this one here. We've got this one here. Oh, that's a big distance. We got this one here. We got this one here. And we got this one here. And actually, what we do is we not just measure the distances, because they could eliminate each other. What we do is we measure actually the squares of these distances. So if we've got some negative distances, they might cancel each other out with positive distances. But if we square it, then they can't cancel each other out. It's the same principle that we used when we did the standard deviation, for example, and the variance. Yeah? So it's exactly the same thing. And what we then do is, and that's usually done through a program, we try to keep this, the squares of distance, we keep that as small as possible. We minimize that. We minimize the squares of the distances. I could show you the equation for that, but it probably would give you nightmares. So I don't expect you to be able to calculate this. And the sum of these squares is actually called the R value. And the definition of the R value is it gives you a numerical value for how good your data points are aligned with a straight line. So, if you got something like that, where your data points are absolutely 100% on the line, this would be a positive correlation, and it has an R value of 1. 1 means bullseye, absolutely on the dot. The R value can take on a spectrum which goes from -1 to +1. +1 means strong positive correlation. Question for you, what do you think does -1 do? It is, exactly, it is a strong negative correlation. What does an R value of 0 tell you? No correlation. So minus 0.8, minus 0.5, 0.5, 0.8. And what you usually have is in this region here and this region, you have strong correlation. So between 0.8 and 1 and minus 0.8 and minus 1, you have strong correlation here. If you are in this region between minus 0.8 and minus 0.5 and this region here, you would consider that as weak correlations. And anything in this range here would be probably treated as lousy. But don't write that. You probably would say very weak correlation or no correlation. Yeah? So, let's see whether you got that. R equals 0.65. What's that? Loud? Weak? What kind? Weak positive correlation. Yep. R equals negative 0.95. Strong? Strong negative. What does that tell you? Numbers are all over the place, no correlation. Yeah? That makes sense? You will see that sometimes statistical programs like Excel allow you to do a best fit line, or what Excel calls a trend line. I have a video on that, how you do that. Have you done trend lines in Excel? Yeah? Some people have, some people haven't. So have a look at this video. And one thing that's sort of what you quite frequently will find is that instead of an R value, which can be positive or negative, sometimes you get an R square value. I don't like R square values because it takes away the information whether it's positive or negative, and also it's an attempt to make data look better than they are, because an R value of 0.9, which is already, which is good. What did I just say? No, the other way around. You would get an R square value of 0.81, and why complicate things? So, but Excel insists on R square value. I don't personally see any advantage of that, but what you will get always from me is an R value. Okay? Now, there is one important thing that I want you to remember, and that is correlation is not, loud, is not causation. You cannot say that because one thing happens, it has, as a consequence, as a direct consequence, as a direct cause, this effect. Let me give you an example. In the late 50s, they did a survey in Sweden where they measured over the years the amount of babies or newborns, and at the same time they also measured the amount of breeding pairs of storks. And what they found was that there was a very strong positive correlation. It looked like that. Number of storks and number of babies. What's your conclusion? We don't believe in, biological processes. It's very evident from this graph that babies are delivered by the stork. The more babies, the more storks, or the more storks, the more babies. Bit of a flaw there, isn't it? Because everybody you ask who had ever had a baby will tell you that it doesn't work like that. And there's the story about when Daddy tells his little son that he got a little brother and the stork delivered the brother. The little son says, "I don't understand what you're doing, Daddy. There are so many gorgeous women out there, but why do you have to have sex with a stork?" So, correlation is not causation. Also, be careful with trend lines, because these trend lines do something absolutely amazing. They predict, in a way, the future. Let me give you an example. In 1970, about 48% of Americans, do we have any Americans here? Hands up, who I could potentially offend? American? Can I offend you? No, okay, good. 48% of Americans had a BMI of larger than 25, which is considered overweight or obese. 1990, this number rose to 58%. In 2010, this number was at 75%. Right? Now you can draw this like that. So here would be the year, and here would be percent overweight. So here that's 1970, that's, what was it, 48. 20 years later, 58. 20 years later, you've got 75. Right? So far, so good. What kind of correlation is that? It's a strong positive correlation, yeah? Now the interesting thing is, if you wait until the year 2060, in the year 2060, every single American will be obese and overweight. Yeah, makes sense. In the year 2080, 120% of the Americans will be overweight. And now you probably think, how is it possible that 120% of the Americans are overweight? Any solution to that? I don't have one either. Yeah? So if you just simply follow a trend line, you have to be very, very careful what this trend line actually tells you. Does it tell me that 120% of Americans will be obese? Then, and the answer is yes, then forget the trend line. It's nonsense. I can only say up to this point here, that's a positive correlation. Does that make sense? Yeah? So be aware that storks don't deliver babies, regardless of what the Swedish statistics say. Also, be aware that you can't switch around dependent and independent variables. For example, you can say, I measure the outdoor temperature and put that in correlation to the amount of sunglasses sold. What would you expect? Let's say it's the UK. Correlation, yes or yes? Yes. Positive or negative? It should be a positive correlation like that. Right? So that means the hotter it is, the more likely it is that the sun is shining, and there is a high probability that I sell more sunglasses. Now let's do it this way round. Number of sunglasses temperature. What do you expect? Correlation, yes or yes? Yes? So that means the more sunglasses I sell, the hotter it's going to be. Is that right? If that was the case, hey, I would sell so many sunglasses, I would flog them just in order for the weather to get better. Yeah? You see, you can't turn it around. And that is where this comes into place again. Correlation does not mean causation. There could be a lot of different factors involved in something. And again, that makes statistics quite interesting. For example, I can measure hours spent on social media versus grades of a student. Positive or negative correlation? What do you expect? It depends on the subject. Well, let's say biology. Negative? Yep, could happen. If you bum around on Facebook and things like that, you forget to study. And that would be the case for a lot of students, let's say, in secondary class. But what would happen if you use the social media to discuss things with your mates? Discuss biology problems. What would you expect then? Positive or negative? It would be probably a positive correlation in this case, because you use the social media to learn something about this topic, right? So it really depends what you do with the social media. It could